Start. Hello, everyone. My name is Can Zhao. I'm an applied research scientist from NVIDIA. I'm honored to welcome today's speaker, Dr. Riqiang Gao from Siemens. Dr. Riqiang Gao is a staff AI scientist in digital technology and innovation at Siemens Healthineers. He is a project manager and a technical leader in radiotherapy planning research at DTI. He obtained his PhD in computer science from Vanderbilt University. As first author, he has published papers in leading conferences and journals about interdisciplinary fields of machine learning, computer vision, medical imaging, and clinical validations, including ICML, CVPR, MICCAI, and radiology AI. He has received multiple awards, including the Innovation Excellence Awards at Siemens Healthineers, the C.F. Chen Best Student Paper Award at Vanderbilt, and twice RFW All-Conference Best Student Paper finalist at SPIE Medical Imaging. He focused on radiotherapy and medical imaging with AI reflects his dedication to advanced patient care. Let's welcome Dr. Riqiang Gao.
Thank you so much, Sam, for the nice introduction. I'm going to share my screen and open the presentation.
Yes, I can see. Yes, I can see your slides.
Okay, very good. Hello, everyone. I'm so excited and honored to be invited to have this talk today. The topic that I'm going to share is AI for faster radiotherapy planning. I also would like to briefly introduce myself and our team at Siemens Healthineers. Currently, I'm staff AI scientist at Siemens Healthineers. I graduated from Vanderbilt University with a PhD degree in computer science and 2022. My main focus is on AI for radiotherapy and medical imaging. You can know me more from this homepage. Our team is from the Siemens Healthineers AI Technology Center. It is the global AI research center of Siemens Healthineers. Our team is mainly located at the US, the Princeton site. We have colleagues in Germany, China, India, Romania, and so on. One of our main missions is to address the hardcore clinical problems with advanced AI technologies. Our team is led by Dr. Doreen Komanichu. You can find a lot of exciting works in this page. Here is a beautiful photo of our building at Princeton. And this is a more comprehensive view of the global locations of our team. It's Princeton in US, Erlangen in Germany, Romania, Shanghai in China, India. Back to the topic today, and this is the content. First, I would like to briefly introduce about the background of radiotherapy and the planning, as well as the scope of this talk. Then I will introduce several AI modules in the planning pipeline, including dose proposal, fluence map prediction, and the leaf sequencing. Some of the versions have been published in CVPR, medical physics, ICML, respectively. Lastly, I will share our view about the generalizability and scalability about the AI for RT planning. I will introduce our organized challenge at AAPM 2025 and a paper about automating high quality RT planning at scale. Let's briefly talk about what is radiotherapy. It is one of the major types of cancer treatment. It is suitable for about 50% of all the cancer patients. The RT planning goal is to let the X-ray focus on directly the cancer target. We also call it PDV, while protecting the healthy tissues and organs at risk from high dose of radiation. And this is just a cartoon figure about how the RT treatment could look like. This is RT machine, and this is a patient lie down on the table, and this is the X-ray comes out of the RT machines. The goal is mainly focus on the tumor ranges, maybe a little bit margin, and keep the organs, healthy tissues from the high dose radiations. Below figures briefly show one round of planning process with the Eclipse system of variant. First, the user need to set up the machine parameters, including the beam angles, which defining which direction the X-ray should shoot, and of course the objective functions for the following optimization. The central part here is the PDV. Many practical cases are, the Frunze field of view just cover the PDV, maybe add a little bit of margin. Then the second step is running the optimization and get the leaf sequence of each control point, basically each time each time point. You can see the leaves are moving, and the gantry is also rotating. The RT planning problem can be formulated as the prediction of a sequential actions. After the MLC positions and those intensities are optimized, then we will calculate the dose, the 3D dose, so we can visualize it in the system. This is a screenshot of the Eclipse system. Eclipse is a product of Varian, and then we can assess the plan quality. In practice, the whole planning process is actually much more complex. For example, after the CT simulation and the contourings of the target, the OARs are done. And of course, the dose prescription is also provided by the clinician. The user will need to create the objectives based on the selection of clinical goals and the patient standards, because the objectives definition is not always consistent. It could depend on the clinical goals, the patient status. Then running the optimization and those calculation, as I just mentioned, and after that, the physicist will review the plan. In many cases, there might be some other iterations needed because the initial plan not necessarily meet the clinical quality. So after that, there would be the final review and approval. This process may take 2 to 10 hours of active work over a period of 1 to 5 days. But the time is very important to cancer patients. So our goal, our mission is to accelerate this process significantly with AI. So imagine what if the planning and the quality checking are interactive, and the planning process is much faster. Imagine the final plan is being derived within just one session, jointly by the dosimetrist, the physicist. So powered by the advanced AI, our goal is to reduce the time of this planning process significantly, for example, less than 2 minutes. Then the radiotherapy could be available for much more patients. Let's talk a little bit more about our AI pipeline. This is a version we already built. There were some new versions we are working on, which is not out of the scope today. But look at this version, it captures well about our scope. Given the CT, the contours of PTVs, OARs, the user selects the bin geometries. The first step is dose proposer. It basically estimates the 3D dose distribution very fast without going to the optimization loops. Second, based on the predicted 3D dose, we make BM projections and then predict the Frunze maps of each control point with another deep learning model. There was, I believe I just mentioned some terminologies which may not that familiar to all of you. I will introduce a little bit more in the following slides. So don't worry about that. After the step 2, at this point, the Frunze maps are still some just the 2D metrics, which is not deliverable with the RT machines. So the third step is to translate the Frunze maps, those 2D metrics, to deliverable machine parameters, the MLC sequence. Then we could use the Eclipse dose computation or deep learning dose engine to calculate the deliverable dose and check the quality. Since there is no complex optimization loops included, this process is much faster than the optimization pipelines. Actually, those AI modules can not only be formulated as this end-to-end solution, they can also be integrated in current optimization pipeline separately. So next, I'm going to introduce more about each module as I just shown. The first one is the dose proposer. So let's first take a look about why we need the 3D dose proposer, 3D dose prediction, you could also say. The advantages of AI dose prediction, there were many firsts, include first, faster inference. So it takes less than 1 second to get a 3D dose distribution. In contrast, the conventional optimization planning need 3 to maybe 30 minutes to get those distribution. Second, the AI dose prediction can be learned from large-scale historical data, while the conventional plan is only trained with fewer samples. So the knowledge space is quite different between those two pipelines. Then the next question is, what can the AI dose prediction do? In addition to, as one part of the end-to-end pipeline, it can be also used for faster machine parameter configurations. Because when you choose one parameter, right, you run the AI dose prediction very fast. You could visualize it and get a sense of how the quality would be. And you may adjust the machine parameters, like the beam angles and so on. And those prediction can be also used for better optimization, better objectives for deliverable planning, because it captures 3D information and it can generate better objectives compared to conventional planning pipeline. And this be also used for quality checking, as it encodes kind of, because it trained with very large scale historical data. It may estimate kind of global optimal plans for the user to compare with the plan that the user just created. So we had a work published in CVPR 2023. We proposed a new type of conditional gain to address this dose prediction problem. In many dose prediction references, researchers focused on relatively simple contexts. For example, only one type of treatment with a fixed beam angle template, for example. Here we have addressed much more challenging context. Basically means that the treatment types can be different. Here I have the S and the D here. S means static, D means dynamic. There were two major types included. And the angles, the beam angles and the beam plates basically describe where the beam could shoot. So the angle template can be also different. And furthermore, this mechanism designed to also dealing with missing data, as some of the data set, they may don't have the complete information, the complete of conditional space. So in this framework, our conditions are very heterogeneous and some might be missing. That's why we call it the method as the flexible multi-conditional game. I know some audience may be curious. Nowadays, the diffusion models are so popular. Why we use GAN? The main issue is actually the inference speed of diffusion is much slower than our current pipeline. Our GAN model can inference a 3D volume with less than 200 milliseconds. We have tried diffusions. So far, we haven't got a version that can run so fast and to get a reasonable prediction. But we will have a intern in this summer to make more explorations. Back to this work, the conditions include the CT and masks, treatment mood, angle planes, beam planes. The CT and the masks are patient data. The selection of planning type, basically the mode, and the missing masks, the angles are the configurations of the plane or the indicators. The network modules include the generator, the pre-trained encoder for the condition classification, and also a discriminator. We have multiple noise functions, include the reconstruction dose, the dose volume loss, and the mode classification loss to enhance the mode feature, and the missing consistency loss, which will be introduced next page, and of course the GAN loss. Let me introduce a little bit about the methodology, right, and how the missing consistency loss play a role here. So given M conditions and their missing indicators, basically means when the condition is missing, the indicator would be 0, otherwise it would be 1. Our adversarial loss becomes like this. It is still a conditional game, but there were multiple conditions and some missing indicators. The G and the D are generator and the discriminator. To let the model be robust to the missing conditions, we introduce this missing consistency loss based on the condition extraction modules. The EI is extraction modules, which extracts features from the prediction based on the condition CI, for example. In short, the missing consistency loss reflects how the predictions related to the observed condition J are consistent when another condition I is given compared to the scenario in which it is missing. So for more details, welcome to refer to our paper, and of course later on we will have the discussion session. So here we show how our dose prediction model allow the user interface to change the planning type and the beat angles. The first column is the reference plane. During the prediction, if we use the same configuration as the reference, the prediction matches well to the reference. Additionally, the user can change the angles and the treatment type. For example, those angles are changed, and here the treatment type is changed, even we are not necessary to provide the angle planes. So the model is still functionable. You can see the corresponding predictions here and showing some DVHs. DVHs is basically some statistical visualization of the dose distribution and related to the masks. This is a dose prediction model we had about 2 years ago, mainly focused on lung cancer. Now we have more robust versions now and a different treatment site. Next, I will introduce the second module in the AI end-to-end pipeline. We call it Fluence map prediction. So first of all, what is the Fluence map? The Fluence map is 2D representation of the intensity distribution of the radiation being delivered to the patient. So I show two figures here. I think this figure, those two figures describe well about the treatment for prostate cancer. The X-ray shoot from this direction, and those are the intensity maps, right? Those intensity maps basically the Fluence maps. So those two figures, so those two figures describe one type of the planning, IMRT. Basically, the gantry is not rotate, but in practice, there is another treatment type called the VMAT. The gantry angle could rotate as well. So in this work, we use the deep learning model to predict the Fluence maps of each control points. So the input to this module is predicted 3D dose about the module that I just mentioned. And there were two major steps. Step one is to project the 3D dose distribution from all beam directions. You will get something like this. Oh, sorry. All the projections will stack will be stacked together as a 3D volume. And then this 3D volume will fit into backbone. The backbone here we use is the MetaNext, which achieves the state-of-the-art performance in the medical image segmentation. And we found it also pretty robust for this task. And the output, the prediction, is the stack of all the Fluence maps. All the Fluence maps means the Fluence map from all angles. Here shows some results. The DVHs are from the dose distribution that is computed from the reference plane, Fluence maps, and the predicted Fluence maps. The dash lines are from the predictions, and the solid lines are the references. So you can see they are matched pretty well, indicating that the Fluence prediction module is working well in this context. So for next, I will introduce the last AI module in the end-to-end pipeline that I mentioned in the beginning. The last module is leaf sequencing. So the topic of the leaf sequencing, you may remember this cartoon figure, right? I showed that in some slides before. This is where the MLC, the leaf sequence locate in the radiotherapy machine. And this is how it could look like in practice. Those leaf sequence movement determines the shape and the intensity of the radiation dose delivered to the patient. So remember the goal of the radiation therapy planning is to let the dose mainly focus on the tumor target and keep the healthy tissue and organs at risk from the high dose. So the right figure shows part of a practical plan in the Eclipse system. You can see the leaf are moving right from time point to another time point, and the gantry is also rotating. This is a gantry, and this is a gantry in this cartoon figure. Let's take a look about how we address this leaf sequencing problem with AI. First of all, the leaf sequencing are needed in both our AI end-to-end solution or an optimization solution. This is an illustration of our AI end-to-end, right? We use the a deep learning model to predict the 3D dose distribution, then predict the Fluence maps. However, in this stage, the Fluence maps are not deliverable. So this module is to translate the target Fluence here to deliver machine parameters. And then we can import the solution to Eclipse and visualize it, calculate those, and so on. For current optimization pipeline, as shown in this figure, right? The component for the leaf optimization can also be replaced by our AI leaf sequencer. Our AI leaf sequencer is built in a multi-agent reinforcement learning context. The target Fluence is the input, which from end-to-end pipeline is actually the output of the last module. The leaf positions, like here, the leaf positions and the those intensities are the output of this module. By interacting with environment, we build environment based on some physical properties. By interacting with the environment multiple times, the leaf actors and MU actors will predict reasonable actions result to deliverable machine parameters, which will achieve a predicted fluence maps close enough to the target fluence map. But this predicted fluence map is deliverable to the machine. In the AI end-to-end experiment, we can see that here the AI solution can achieve a similar solution to compared to the Eclipse optimization solution, but with much less time, from many minutes to seconds. In the optimization engine, as I just shown, when our AI solution is integrated, we can see a faster convergence of the optimization, especially in the early stages, which can reduce the optimization time as well. In the future, we plan to expand the scope, for example, training end-to-end, enable the planning quality as some learning reward, which should further increase the planning quality and still running very fast. Let's go to the last section. I'm going to describe some intentions on the generalizability and the scalability about AI for RT planning. I will introduce our organized challenge at AAPM 2025 and a paper about automating the high quality planning. So up to now, I have introduced some technical modules in the RT planning. In the meantime, actually, we are shocked by a lot of advanced AI works from other domains. I believe most of the audience are familiar with the computer vision, the medical image domain. Recently, many successful AI models are built on very large scale training data, like the stable diffusion, segment anything models, DALI, and so on. Their training data scale is from millions to billions. However, training data from RT topics are still very limited. Most of existing works in the RT planning domain, especially with AI, are basically about 1,000 or even fewer treatment plans. So which is significantly smaller than the data scale used in those representative successful AI models. So existing RT models can be successful when the scenario is simple. For example, if it is just one treatment type or just one treatment site, and the beam angles might be fixed and so on. However, this kind of data limitation problem can present significant barriers to the next advanced generation of RT planning, which we believe it would be generalizable and robust AI models. So we aim to bridge the data gap between the RT research and the vision domains. So we built a pipeline to automate the high quality RT planning, which could be, at least we believe, which will be very helpful for training large scale AI models. This is This is an illustration of our pipeline. There were many 4 modules. The first one is AI contouring. We use Siemens Healthineers AI Red Companion to do the organ segmentation and then create hyperstructures with the rule-based methods. And we keep the clinical PTVs and with the state-of-the-art rapid plan model, we configure the machine, we configure the planning machines and defining the objectives. Then we will run the optimization and the dose calculation with the Eclipse system, and then check the plan quality, and after that automatically adjust the objectives. Basically simulate how this process would be conduct in practice, but in an automatic way. So for more details, please refer to our paper. But with this pipeline, we can create high quality plans automatically. Of course, we need the Eclipse system and the GPUs to make it scale. This is a comparison between our released data set and another closely related work called the OpenKBB. So this is a table showing some properties, right? Like the treatment site, the OpenKBB only focused on one site, and we have multiple sites included. The prescribed doses for OpenKBB is fixed, and ours are variable. The number of PTVs, we are all up to 3. The planning tools, they use a pretty old one, and we use a new version of Eclipse optimization. The number of plans of our released dataset is more than 10 times compared to OpenKBB. And we also released more data. More data means that our data are released in the DICOM format, and we also have the processed data format included. So the researchers can use those data to many different topic for research. Oops. So also with the released data, we host we host an AAPM challenge this year. This challenge is led by Siemens Healthineers, and we co-organized with Varian, UPenn, UCSD, and MSK. The task in this challenge is generalizable dose prediction with just one model. And this one model should cover multiple treatment types and multiple treatment sites. I believe this challenge is a successful one. We saw many exciting solutions, and the winners have been announced in our GitHub repo and the challenge website. Now the challenge is not officially accepting new solutions, but the post-challenge evaluation is still open, so researchers can still test their model with the platform. So if you are interested in this topic, welcome to take a look at this challenge. Okay, here comes to the end of my presentation, and this is listed. This is a list of public works that I have just shown. My apologies, due to the limitation of time, I cannot go to too much details, but welcome to discuss even offline. Thank you so much all for your attention. I'm here for any questions and comments. Thank you so much.
Thank you, Riqiang, for the wonderful talk. So now it's the time for the questions. I can see we already have questions in the Q&A tab. So let's start from the first question. Have you tried diffusion models with only 10 steps with DPM solver? Actually, I have the same question as actually NVIDIA has open sourced a solution that can accelerate diffusion models a lot.
Yeah, to be honest, I haven't put too much effort, I mean, by myself, right now for the diffusion models, but I know there were some exciting diffusion models that is also very fast, and I know the MICCAI model from NVIDIA. We actually some colleagues at our side tried the model for different tasks. For the DPM solver, honestly, I haven't tried that. As I just mentioned, that we will have an intern coming to explore more in this space. But I think I will take a look about what is the DPM solver offline. Thank you so much.
Thank you. Looking forward to it. Second question. Thank you for the interesting presentation. My question is about the reasons for using GAN and reinforcement learning in the project you have presented. I may have missed some of your details, but what are the justifications of using them? Are they based on theoretical, intuitive, or empirical experimental basis? Thank you.
Okay. Thanks for this great question. I think this is kind of a high-level question. Why using GAN? Why use reinforcement learning? So maybe I can go back a little bit to just showing the AI pipeline, the figure. Just 1 second. Maybe I can just use the slide here. So the first step, what we're trying to do is estimate the 3D dose in a very fast way, because we don't want, with the AI, we don't want to go to the many iteration optimization loops. So the task is basically 3D image generation. So the GAN is a kind of a default option for me. I have the background of GAN. I also did some works in many years ago. I tried it and it worked pretty good, because we want the prediction matches the reference plane, which means that the predicted 3D dose distribution should be realistic. As I mentioned in previous slides, this 3D dose proposal not only used for this end-to-end pipeline. It could also for the user to check the plane qualities and so on. So it should be a realistic distribution overlaid with the CT, with the masks and so on. The second part about the reinforcement learning, why we use that. So I think I mentioned this a little bit. This multi-planning problem is actually the prediction problem of a series of actions. So when we try to predict a series of actions, the reinforcement learning comes to my mind. So we formulate the especially the final step, the leaf sequence. So then we predict how the leaf positions moving at each time point, of course, as well as those intensities of each control point. So the short answer is because this is a series of actions to be predicted, and I believe reinforcement learning is a good choice to start.
Yeah.
Thank you.
Thank you. The next question is from Ignacio. Thank you for such insightful presentation. The radial sensitivity of different organs at risk is different throughout the body. So usually the dosimetrists plan accordingly. For example, spinal cord versus regular muscles, is that accounted for in the optimization cycle for the leaf optimization? Thank you.
So let me I also reading the question. Let me try to understand it more deeply. So I think your question is for different organs at risks, right? They may have a different tolerance threshold for the organ intensities. So for this context, both the optimization cycle and the leaf optimization should take this into account. So the optimization for the RT planning, there would be a very long list of objectives. For example, they would put a threshold. Let's say for the spinal cord, the maximum dose couldn't go beyond, I don't know, 30 gray, something like that. For the regular muscle, for the regular muscle, they may put a higher threshold, which means that the highest dose, I just give an example, cannot go beyond 40 gray, something like that. So after this kind of optimization goals are set, then the leaf positions, the leaf optimization will act correspondingly. It will try to avoid the spinal cord more than the regular muscles. And for our AI solution, right, we basically trying to mimic how the optimization do, but with a much faster fashion. I hope this answered your question.
Thank you. The next question is from Bowen. Treatment planning in radiation therapy is an offline task. Do you think diffusion models can have a better performance if we can accept them to be a little bit slower?
Treatment planning is offline task. I'm not exactly sure what the offline means here. Okay, maybe you mean that it is not planned during the treatment. Yes, that's true. So the planning is made in advance. So the diffusion model can play a role here if it can be increase the increase the accuracy, increase the plan quality. So for example, as I mentioned, right now the first module here, if we only talking about the AI module, the AI forward, now it takes like less than 200 milliseconds. I think this time can be more. So in practice, the we try to make it very fast, but the overall pipeline, eventually it would be several seconds. So for example, if a diffusion model can have a much better impact in this part, but it may be a little bit slow. Let's say it takes 3 seconds or even 5 seconds. I think that's totally fine. So because in practice, right now, the optimization pipeline, as I mentioned, it takes 3 minutes to 30 minutes. So increase like 3 seconds doesn't matter too much.
Yeah, thank you. What if the diffusion model takes 2 minutes? Just like an example, 1 to 2 minutes. Is that acceptable?
I mean, I would like to leave this decision to the product team. But personally, I believe 2 minutes would be a little bit too long. So we hope at least it could be less than, I don't know, 10 seconds.
I see. Thank you. The next question is from Arvalo. I missed the quality assurance step in the process description. You still need to test your plans on phantoms before treatment?
So this because this we are talking about AI solution, right? We are talking about apply radiotherapy to real patient to basically what I'm trying to say is we need to put kind of a safe check, a quality check before applying any solutions to treat a patient. We are talking about the radiations. We don't want this go wrong. So then my answer to your question is either from a optimization pipeline or AI pipeline, we would always need the plan quality check before treatment. Yeah.
Thank you. The next 2 questions from Sebastian. How do you make radiotherapy articles, which are a very applied domain, publishable in more CV conferences like CVPR, Europe, etc.? The second question is the dose maps you predict do not consider the different types in the patient body, right? The body is considered as water.
So let me try to answer the first question first. So for those CV conferences, they I always found they will be a track that is for applications, especially for healthcare medical applications. I think not only for this kind of the radiotherapy topics, many other related domains in medical imaging can also submit to CVPR, NIPS, and so on. So I appreciate that. I mean, because this is about AI, and right now there are many scientists focus on AI for science, AI for healthcare. So I think it is very important to have people from different background meet together, share their thoughts. I think this will just make those domain in a better place. The second question, the dose map predicted didn't consider different types. Different types, I'm not very sure what does that mean.
Maybe attenuation rates or just guessing.
The body is so I can describe a little bit more about the context, right? So the input includes the CT images the CT images basically because the HU value of the CT, right? The model will have some understanding about the tissue or water or air in that location. So those information will be included in the CT. And we also include the masks. The mask is basically the segmentations. The segmentations of the tumor location, PDV, and also the organs at risk. Next, for example, here the lung, the heart, and so on. So since those information are included, then the planning pipeline will try to avoid those organs at risk and focus more on the tumor part. So you mentioned that body is considered water. I don't think so. The body is just the body of there would be a body mask. Since the body will include the whole patient, so it wouldn't be considered as water.
Thank you. Next question from Jing. Hi, did you compare the results that when the training data does not contain beam angle information?
A great question. So actually in the study that we published in the CVPR, so for some scenarios we didn't include the beam geometries. It depends on what kind of context you want to test the model. For example, if you know all the testing patients are using homogeneous type of treatment. For example, all the angles are fixed, or they always use full angles treatment. Actually, this is the context that used in the OpenKBB relative work that I just mentioned. But if we are talking about practical scenarios in which that the beam angles can be different, especially for lung cases, because the lung tumor can be anywhere of the lung, right? So in this kind of context, the beam angles are important. Without giving the beam angles, you can never get the right dose distribution.
Thank you. Next question is from Elias. May ask you, how do you feed the results and outputs of the Fluence to MLC module into Eclipse? Does it work over ESAPI? Do you use any other interface to Eclipse TPS?
Yeah, thanks for the question. So two ways. One way is we save the leaf sequence, basically the outcome of the AI end-to-end solution, right? Save them as DICOM. Then we upload the DICOM into the Eclipse system. So the Eclipse system will read the DICOM and do whatever necessary calculation and show the dose. So this show the dose as well as the leaf sequence. This is one way. Another way is yes, we could use ESAPI. Actually, we use ESAPI often when we interact with the Eclipse system. This is a very important part in our simulation pipeline. the last session that I mentioned, automating the planning and scale. Yeah.
Thank you. The next question is from Kasam Zomart. I am not that familiar with the radiotherapy, but I guess you have to apply for approvals like FDA approval. So my question is that, are you planning to get it? Or have you already get it approved, or are you already using it in practice?
Great question. So what I showing here, and I also put the statement on each slide, right? Those works are just research results. We haven't put those into product yet, and the future availabilities cannot be guaranteed. So the FDA approval is mainly for the product. For what I shown here today, we haven't got FDA approval yet. But of course, this is our goal, and we also keep working on that, generate more advanced visions and so on. Yeah.
Thank you. We have one last question from Sebastian. Is the dose predicted by the model impacted by the CT scan input? Like if you just train a model without the CT scan, just the mass, does the model predict as well?
That's a very good question. Actually, we tried that. It depends. Sometimes when you include the CT, include the CT compared to without the CT, the difference is minor. Sometimes it may make big difference. I want to say big, but it will make a noticeable difference in some context. So this is really depend on the scenario, and this is those are based on empirical result. But in theory, since the CT includes all the informations, more comprehensive informations, more than what in the contours, right? So it depends on how you train the model. If you train the model in way that trying to utilize the CT information, then the CT will make an impact. Thank you.
Thank you. And thank you, Riqiang, for the wonderful talk, and thank you to all the audience for joining this talk. If we get the permission from the speaker, we will put the video to our YouTube channel, MICCAI Industrial Talk. Thank you so much.
Thank you. Thank you, Sam.
Bye.
Bye-bye.